In the next part of this lesson, we will cover the snow model and its components and discuss how it is being used in the flash flood guidance system. For geographic regions that experience snowfall, the FFGS provides products that estimate the condition of the snow in each basin. These products include an estimate of snow water equivalent, in short SWE, the amount of melt released from the snowpack in each basin, the aerial snow cover, and mean aerial temperature. The purpose of the snow model is to keep track of the evolution of the snowpack. The precipitation is divided into rainfall and snowfall. The snowfall is being accumulated in the snowpack. The snow model keeps updating the energy state of the pack and generates melt that, together with the rainfall that occurred on surfaces that are free from snow, contribute water to the soil model. For the FFGS, we use the Snow 17 model in order to track the snow accumulation and ablation in all of the basins. Snow 17 is an energy and mass balance model that, as the SAC SMA, was developed in the mid-1970s and is being used as the operational model by the US National Weather Service. The following is a list of relevant references that describe the model in details. Let's start by emphasizing the importance of simulating correctly the snowpack and the interaction between the soil water content and the snowpack evolution. An example of the seasonal relationships between the snowpack and the soil water content is nicely demonstrated in the example below. This example is based on observations that are taken from a site at the Sierra Nevada, California. This region has a seasonal winter snowpack that completely melts during the summer. The snowpack, indicated by the black line, is being accumulated during the winter, December through April, to peak in April and completely melt by June. The soil water content at the upper layer, the red line, gradually increases during the winter, likely because of melt that occur at the interface between the soil surface and the snowpack. In this region, the soil temperature rarely freezes, and therefore, because of the warm soil temperatures, some melting occurs at the interface. Following the peak of the snowpack in April, the deeper soil water content increases, the blue solid line, to peak just after the snow was completely depleted. The upper soil water content is also peaking when the snow is depleted. In this region, the summers are usually warm and dry, and the soil dries completely by the end of the summer. It is seen that in this region, although precipitation occurs mainly during the winter, the highest risk for flooding because of the limited capacity of the soil to absorb additional water is during the spring. In order to estimate the melt from the snowpack, we need to calculate the energy balance within the snowpack and account for all the energy fluxes into and out of the snowpack. These energy fluxes include radiative fluxes of short-wave radiation and long-wave radiation, turbulent fluxes of sensible heat and latent heat, heat conduction at the ground-snow interface, and the heat transfer during event that rain is falling directly on the snowpack. Unfortunately, applying detailed energy balance model can only be done in locations that have meteorological observation of variables that represents these energy fluxes. These are rarely available in a regional scale and in a sufficient density that warranted regional applications such as the FFGS. A simplified family of models are models that rely on air temperature, which is a commonly observed meteorological variable, as an index for the energy fluxes. The Snow 17 is a conceptual, spatially averaged energy and mass balance model that is being applied to each basin of the FFGS. It is a single-layer model that uses air temperature to estimate energy exchange across the snow-air interface. In addition to temperature, the only other input variable that is needed in order to run the model is snowfall. The snow model simulates and updates the following snow state variables: snow water equivalent, snow liquid content within the snowpack. The snowpack has the capacity to hold some of the melted snow, and this liquid can possibly refreeze. Meltwater is leaving the snowpack only when enough melt occurred to satisfy the snowpack's water holding capacity. Another state variable is the snowpack heat deficit. The model keeps updating the energy state of the snowpack by updating the heat deficit variable. Heat deficit is the energy that is required to bring the snowpack to 0 degrees Celsius. At 0 degrees Celsius, additional energy to the pack causes melting of the snow. The model output is the melt that leaves the snowpack. The formation of snowfall is dependent on the vertical profile of the temperature from the cloud to the ground surface. The precipitation phase, solid or liquid, can be observed in weather stations. However, in extensive area, it is common to use meteorological indicators to estimate the phase of the precipitation. Most widely used meteorological indicator is the 2-meter air surface temperature. Studies have been conducted in different regions to derive an air temperature threshold for which below it the precipitation appears the ground as snow. The phase transition of snowfall and rainfall occurs over a wide range of temperature, from, say, -2 degrees to +2 degrees Celsius. It is common to select this index as the temperature in which 50% of the precipitation appears as snowfall. As seen in the figure, for this specific site, it occurs at 2 degrees Celsius. In the FFGS, the mean aerial temperature is estimated for each basin by combining two sources of data. The first is real-time temperature reports from weather stations. It can be seen that the distribution and availability of station reports are largely varied for different regions and countries. The second source of temperature data is available from the Global Forecast System, GFS, of the National Centers for Environmental Prediction, NCEP, at NOAA. The GFS forecast is available at 0.5 degree for the entire globe 4 times per day. The aerial snow cover estimate in each basin is presented as percent aerial cover. The white areas in the figure are basins that are completely covered with snow, and the brown colors are basins that are free of snow. The blue colors indicate partially covered basins. The information of the snow cover is available from the Snow Aerial Cover product named the Interactive Multi-Sensor Snow and Ice Mapping System, in short IMS. This product is made available by the National Snow and Ice Data Center. It is a daily 4x4 km snow cover product that is based on information from Polar Orbiter and geostationary satellites using optical and microwave radiometers. We now completed the lessons about the soil and snow models and the way they are implemented in the FlashFlood guidance system. Thank you.